Hi, my name is Seth, and today I'm going to be telling you a little bit about buffers. So, for starters, what is a buffer? Well, it's a conjugate acid and a conjugate base mixed together, which is another way of saying a weak acid and a weak acid that's lost its proton, all in the same beaker. So an example of this might be, CH3COOH and CH3COO-. See how the proton is here and how it's missing on this side. This is the conjugate acid, and this is our conjugate base. Now what does a buffer do? It keeps the pH from changing as much as it would if the buffer wasn't there. And how does it do that? Well, there are two reactions that can go on in a buffer. Let's say I add some strong base to something that's buffered. Well, that strong base is going to react with the weak acid to make weak base. And what if I add some strong acid? Well, that strong acid is going to react with the conjugate base, this A-, to make conjugate acid. So that's the concept. The concept is easy. The harder part is figuring out what the pH is. And that's why we're going to go through one of your book problems here. Now the important thing to remember is that even though there's a lot of stuff here, there's a lot of stuff here because I'm trying to show you a few of the tricks. So if you go and look in your textbook, this is question 19.39, and the word of it is something like you want to titrate 20 mils of 0.1 molar butanoic acid with 0.1 molar NaOH. So that's the Ka of your butanoic acid. That is a very important number. And then there are a bunch of different volumes of NaOH being added, and you need to find the pH at all of those. I picked the pHs where we can use different tricks every single time. So, let's get started. Your first one is before you've added NaOH at all, and that is over here at A. Now in this case, remember, all I have is conjugate acid, that butanoic acid that I started out with. So really, all I need to do is treat this like a weak acid problem, build my ice table, and I'm done. I can use this, solve for x, take the negative log of this to get the pH. Okay, so what about this second part? Well, here I've added 10 mils of NaOH solution. So if I go and look on my overall pH graph of what's going on, I'm right here. I'm halfway towards the equivalence point. And because I'm halfway there, because I've used up half of my conjugate acid, I can use a nice trick. Now, to use this trick, you need to remember Henderson-Hasselbalch, which is pH equals pKa plus the log of A- over HA. Now, when I'm halfway to the equivalence point, the concentration of A- and the concentration of HA are equal, which means that this ratio here is equal to 1, and the log of 1 is 0. So actually, in this case, pH is just equal to pKa. So far, we haven't really had to do any work. That's going to change a little bit. This third question is when we're at 15 mils of NaOH added to our solution. And if you look over here, this method is good for this entire region of our titrating thing. Anything before the equivalence point, you can use this method for. Even the places where we used our tricks, I just like using the tricks because it saves time. So the first thing we need to do is find the initial moles of our conjugate acid that were present. Now I've done that here, and I've also gone and found the moles of NaOH that we added. Then I'm going to set up a table where I keep track of what's going on. This is my overall reaction right now. Remember, I started out with conjugate acid, I added strong base, and that's going to make conjugate base and water. Now remember, I never care about water, so I'm leaving it out. Then I go through and I subtract out the smallest number that I have here. So everything loses 0.015. And I'm left with this concentration of conjugate acid and this concentration of conjugate base. Now because this is a buffer, there is conjugate acid and conjugate base, I can just go ahead and plug these numbers into the Henderson-Hasselbalch equation. And when I'm doing that, remember, these numbers are moles. I'm cheating, but it's okay because it's a buffer. So I can use this and solve for my pH over here. Now the fourth thing we're going to do is find the pH of this solution at the equivalence point. This is after I've added 20 mils of NaOH to my conjugate acid solution, which means all of my conjugate acid has reacted to turn into conjugate base. And I've gone and written that down here. Now remember, it's a 1-to-1 ratio in terms of the stoichiometry. So that 0.02 moles of conjugate acid that I started out with, that's the 0.02 moles of conjugate base that I have right now. I can go ahead then and treat this like a normal weak base problem. And I've done that for you. I plugged in all the numbers. I even found a Kb down here. That's where this number came from. So that part is pretty easy. Now this last part, E, that works for everything after the equivalence point. So look at our graph up here. This is where we are right now. With E, I have over-titrated. I've gone 1 drop of conjugate base past the equivalence point. Now, remember, we just found out that at the equivalence point, all of the conjugate acid has turned into conjugate base. So you would think that the conjugate base has something to do with the pH of this solution, but it doesn't. As soon as I go 1 drop past the equivalence point with my strong base solution that I'm adding, the conjugate base doesn't matter. So I haven't even written it down over here. All that matters is the NaOH that I added. So I went through and I figured out how much NaOH I actually had. Remember, most of it reacted with my conjugate acid to turn into conjugate base. So I've gone through and I found those numbers down here. This is the amount of NaOH solution in terms of moles that I have right now. And I've gone through here and solved for the concentration of OH minus. So then I can take the negative log of this number and use that to find the pOH, and of course 14 minus pOH is pH. Okay, so that's all I have to say for now on buffers. There's a lot of stuff here. Remember the shortcuts, and you can always save yourself some time.